Okay, so for this fourth and final video for 3.1, we're going to do something totally different, and we're going to talk about a math skill that is required of you for AP Physics 1, and it has to do with thinking about graphs and trying to force them to become linear graphs. This is a skill that can happen in any unit of this course and any course where there's equations that you're analyzing. But I didn't want to put it in the first two units because those two units are quite expansive. This one has a little bit more room in it, and so we're going to talk about making and analyzing linear graphs. Now, you are going to need your Unit 3 packet as well, because I wanted to do a couple extra examples of this, and so in addition to taking notes, I want you to find this page, Assignment 3B, What to Graph, and I'll go through just a couple examples from this sheet really quickly later. So find that and let's save that for now. So basically, like, this concept is something that you're going to have to do probably once on the open response section and maybe once on a multiple choice section. And it is based around taking experimental data and making that data into a linear fit, no matter what the equation is. So if you look at all the equations that we have in physics, we have some linear relationships between variables, but we also have very many like quadratic or inverse relationships between variables as well. So we are fitting any equation in physics into this y equals mx plus b format, and then the reason that you're going to do this on the exam is so that you can not rely on a powerful program like Excel or Desmos to fit the data yourself. You're going to have to do this kind of the old-fashioned way. And so here we go. So the way this works is we imagine an experiment has been conducted and that we have a set of data where there's two variables that we have recorded. And so in this first one, we're going to start with something familiar to this unit. We have data on kinetic energy at various speeds. Now, this experiment is kind of a farce because there's no kinetic energy measuring device that exists. We would have to measure mass and speed to get that. But we're just going to imagine that we have kinetic energy and speed data for an object. In other words, we record we like set an object at a certain speed, and then we record its kinetic energy. The way that data tables are set up is we have the independent variable on the left, dependent variable on the right, and so that will continue on throughout this. It's a nice chance to review variables also. So we're going to have to graph this data and determine the mass of the object. So here's what I'm going to do. I'm going to write k equals 1/2 mv squared on one line, and underneath it I'm going to write y equals mx plus b. Now, the variables have to be related to the things you're going to graph on the y and x axis, right? Like the place where variables go on a graph are the x and y axis. So the way this equation is laid out, kinetic energy is kind of matched up to the y axis. So I'm going to, what I'm going to do for my linear graph making is on the y axis, I'm going to graph kinetic energy. That's nothing spectacular. Now, the other variable I have is speed, and it's speed squared instead of just speed. So I'm going to put that as my x-axis variable. So here's where like the linearization comes into play. I'm going to make this a linear graph by graphing the data in a specific way. I'm not going to graph kinetic energy versus speed. I'm going to graph kinetic energy versus speed squared. And that's going to involve some work, but it's just fine. The last things I have to worry about are the slope and the y-intercept. So the slope is whatever is multiplied by x, and in this case, it's what's left over in 1/2 mv squared. The slope of my linear graph is going to be equal to 1/2 the mass. So if I find the slope of this graph that I'm not going to make on this video and double the slope, I will get the mass. And then there's like, you have a y-intercept, and there's nothing in the equation left. And so the y-intercept is 0. And so this should make physical sense. This equation is for kinetic energy, and if there's no velocity, then there's no kinetic energy. So speed is required for an object to have kinetic energy, and so if there isn't speed, there's no kinetic energy. All right, so we're not like doing this in practice, but if I then made a graph, I would have to do some calculation, right? If I had data on speed and kinetic energy, I would just graph the kinetic energy data on the y-axis, but I would have to square all of my speed values and then graph that. They would then arrange themselves linearly because of the relationship that we know between kinetic energy and speed. And again, the slope of that line would be 1/2 the mass. So I could find the slope, I could set it equal to 1/2 m, and then I could find the mass. So that's kind of the pattern we're going for. It's very strange. It's not something that you do in math class, but it is a great way to analyze data without the use of some powerful spreadsheet program and using like good physics intuition. Okay, so the next one. We have data on position and time for an object at rest, and we want to determine acceleration. So time was our independent variable, position was our dependent variable. We have this really long equation for position and time. And if I wanted to determine acceleration, this is the equation I would need to use. This equation needs to be simplified a little bit. This object started at rest, and so the initial velocity times time is going to be 0. So I'm going to rewrite this once, and I'm going to rewrite it in a way that is going to be conspicuous. I'm going to rewrite it as x equals 1/2 at squared plus x naught. And then underneath it, I'm going to write y equals mx plus b. And so again, if I take data on position and time and there's acceleration, I'm going to get a curved graph. You know this from the kinematics unit, that I would get a graph that is quadratic because position varies with the square of time. But I want to make a linear graph. So I do the same thing I just did. I'm going to circle these two. And so on the y-axis, I'm going to graph position. I'm going to circle x, and then I have data on time, so I'm going to graph the time data on the x-axis, but I'm going to graph not time, but time squared. And that means that my slope is going to be whatever's left multiplied by time squared. So slope is going to be 1/2 acceleration. And I chose this as my second example problem because now there is something that can represent the y-intercept. So y-intercept is going to be equal to the initial position. If I release this from rest, there hasn't been any time to accelerate, and so wherever the object started, that's going to be the y-intercept of that graph. And so again, it's going to be very similar to this graph. I just make a graph of position versus time squared, and then that is going to be a linear graph where the slope is equal to 1/2 a. So I now want to transition to your packet, but that's the main skill, is like taking a look at what the variables are, figuring out what equation relates those two variables, and then deciding how to graph them. So Going to the packet, I'm going to pick two things from this table. You can read this later, but basically this table says, here are some variables that you have data for. Here's the equation that relates them, and then you're going to fill in what do you graph and what the slope is equal to. And you've seen the same relationship twice, and so I'm going to do two equations here that don't work out the same way. This next one is for the electric property of resistance. And so resistance and area are two variables that you have. And so I'm going to fit them into y equals mx plus b format. I'm not going to do any circling, but I am going to, it's obvious that r is in the y-axis position. So I'm going to graph r on the y-axis. And then if a is my variable, a is in the denominator. I can rewrite this as that little letter p is the letter rho. So rho times L times 1 over a. And if I think about that like y equals mx plus b format, this is the slope and this is the value of x. So I'm going to graph resistance, or R, versus 1 over A. And that's what I would do, because R and A have an inverse relationship according to this equation. So I would graph R versus 1 over A, and that would give me a straight line graph. The slope of that graph is related to rho times L. Rho in this case is equal to what's called the resistivity of an object, and then L is the length of the object. So that's a weirder example, I guess, or a different example. The last one is T and K. This is tau, actually, because this is period. We learn about springs oscillating later in the course, and this is the equation for the period of an oscillating spring. Again, period is in the y-axis position, so I'm going to graph period on the y-axis. And then if K, the force constant of the spring, is the other variable, I kind of want to rewrite this. I'm going to rewrite it as 2 pi root m times 1 over, whoops, that was not the symbol I wanted, 1 over root k. I'm going to write that one more time so you can actually read it. 2 pi root m times 1 over root k. I can separate that radical into the numerator and the denominator as long as I put the 1 over root k there. So what that means is what I'm going to graph between period and k. So I'm going to graph period versus 1 over the square root of k. If I actually had this data, I'd have to take every piece of data for force constant, and I'd have to take the square root of it and then take the inverse of that. So 1 over the square root of every force constant data piece that I had. And then what's left over is the slope. So 2 pi root m would be the slope. And so this is just a couple examples of how this works. You can rearrange these equations any way you want and graph whatever funky variables you want and still be able to fit it into a linear fit. And so that's the first exploration of this. We will definitely do some stuff with this in class.